for All About Circuit Summit Series 2025. My name is David Peterson. I'm the Director of Engineering Content here at EE Tech, and I'll be your moderator for our next session. Really quick before we get started, I want to announce the giveaway winners for the Conga Tech keynote session that just wrapped up. So Raymond Chin and Douglas Turnbow. We'll be in touch with both of you within the next week to make sure that we have the information we need to send you the giveaway package. Back to today's session, it's titled Smarter Medical Imaging with COMs. Our presenter today is Željko Lončarić. Željko is a market segment manager for infrastructure at Conga Tech. Prior to joining Conga Tech in the mid-2010s, he held various positions within international companies in product management, marketing, and sales marketing in Germany and Australia. Željko holds an MBA in business management and a degree in media technology from the University of Deggendorf, and also he's a Bosch-trained electronics technician. Following today's presentation, we'll have a live Q&A with Željko. We encourage you to submit questions at any time during this session using the Q&A box that you'll see over on the right-hand side of your screen. And additionally, a copy of the slides will be available in the Handouts tab near the end of the presentation. Thank you so much for joining today. And with that, I'll hand it off to Željko for the presentation.
Thank you for joining and a warm welcome from my side. Today I'd like to show you how smarter medical imaging solutions can be realized with computer models. We will explore how modular embedded computing brings more performance, efficiency and flexibility to modern medical imaging devices and what changes with AI at the medical device edge. My name is Željko Lončarić and I've been working in the embedded computing market for 20 years in various roles across product management, marketing and market intelligence. This slide gives you an overview of today's presentation. We will start with the concept of computer models for medical imaging and take a closer look at how GPUs and NPUs, graphic processor units and neural processor units enable AI acceleration. Then I will show an example of AI-supported ultrasound examinations and discuss how to balance performance and efficiency in medical devices. We will also compare deep learning and inference in medical imaging and review some performance benchmarks. Finally, I will give you a brief outlook on software and tools and our A-Ready platform for faster application developments. Artificial intelligence has been a driving force in life science research for decades. What has changed in recent years is that AI has become much more accessible and practical for everyday healthcare applications. This means it is now actively improving patient care, helping doctors accelerate diagnosis, research and decision making, and also increasing the operational efficiency of hospitals and medical facilities. Medical has understood the potential of AI the fastest and implemented it the quickest, because this industry has both the strongest need for accurate and timely diagnostics and the longest experience in working with large amounts of data. This is why medical imaging today is clearly ahead of many other industries in terms of AI maturity. Here you can see the basic concept of computer models for medical imaging. At the heart of the design is a processor model, which provides all the standard PC functions with CPU, GPU and NPU. This model is combined with a carrier board that can be fully customized to the needs of the device in terms of size, interfaces and specific features. The carrier board can be designed from the customer or also from a company like Conga Tech. And we also provide a training to design your own board. Another advantage is the flexibility in GPU integration. Depending on the application, the GPU can be onboard, soldered or plugged in as a module. This modular approach makes it possible to address many different imaging modalities, from endoscopy, ultrasound to X-ray, CT, MRI and PET. And by combining x86 and ARM architectures, we ensure maximum flexibility for different performance classes and use cases with different computer modules. On this slide, we compare GPUs and NPUs and look at their roles in medical imaging. GPUs, or graphic processor units, are traditionally designed for graphics, but they have become the standard for heavy AI workloads because of their very high throughput. They can process the largest number of images per second. Examples include here in the pictures the NVIDIA Quadro for maximum performance, the Intel Arc series as a good balance of cost and speed, and the Hilo 8 for energy and cost-saving applications. NPUs, or neural processor units, are different. They are optimized for low latency tasks and lighter AI workloads with maximum cost savings. The big trend we see today, especially at the edge, is the integration of NPUs directly into processor modules. This allows us to achieve medium AI performance, benefit from optimized AI software, and gain significant cost and energy advantages. In summary, GPUs remain the choice for the heaviest workloads, while NPUs provide an efficient solution for real-time AI at the edge. Ultrasound is a great example of how AI is transforming medical imaging. We currently see a strong shift in the market. Instead of relying on large dedicated GPU cards, more and more devices are moving to processors with integrated GPU and NPU. With this approach, AI can support real-time ultrasound examinations. The system automatically detects cross-sectional measurements, highlight improved color markers, and deliver a much more precise and efficient analysis. For medical imaging devices up to the medium performance class, this means we no longer need a separate GPU accelerator card. Thanks to integrated iGPU and iNPU, we can achieve up to 20% higher AI performance while keeping systems more compact, energy efficient, and cost effective. This is a clear step towards smarter, faster, and more accessible diagnostics in everyday clinical practice. Let's have a clear look on the integrated components of the processor. So this slide shows the balance of AI workloads between GPU, NPU, and CPU, and how each of them contributes to performance and efficiency. GPUs are designed for massive parallelism. They are perfect for graphics, heavy or very demanding AI applications, offering high throughput and accelerating large-scale calculations. The NPUs, on the other hand, are optimized for efficiency. They are built for AI algorithms that run with low power consumption and are especially strong in pattern recognition, for example in speech, image, or video changes. Their architecture is inspired by neural networks, and they are optimized to work with low precision formats like integer 8, which make them very energy efficient. CPUs, on the other side, remain the most versatile part of the system. They focus on sequential processes and are optimized for control, decision, logic, and running the operating system, all with very low latency. When you combine these three elements in a system on chip, you can get the right balance of performance, efficiency, flexibility for medical applications. This slide highlights the difference between deep learning and inference in medical imaging. So deep learning refers to the training phase. Here, large annotated datasets are used to develop and train a model. For example, a model that can detect tumors. This requires very high computational effort and typically relies on higher performance GPUs or TPUs. Inference, on the other hand, is the application of the trained model in real time. Instead of large datasets, It works with individual new data, for example, analyzing a single ultrasound image while the examination is happening. The computational demand is much lower, so inference can run directly on CPUs or integrated NPUs and GPUs inside the device. The benefit of inference in medical imaging are significant. It enables real-time diagnosis during an ultrasound. It supports radiologistics and rapid decision-making, and it improves both the precision and the speed of disease detection. When we look at AI performance in medicine, it quickly becomes clear that the requirements are very diverse, and that makes it difficult to find the perfect solution for every application. For CT or MRI analysis, the most important criterion is throughput. The system needs to process very large amounts of image data, so higher images per second means better performance. In real-time ultrasound, latency is the key factor. Here it's all about minimizing the time between request and response, because doctors need immediate feedback during the examination. And when we talk about mobile diagnostic devices, efficiency becomes the priority. These systems must deliver reliable AI performance over long periods of operation with the lowest possible energy and cost consumption. So depending on the medical use case, the focus shifts between throughput, latency, and efficiency. And the challenge is to balance these requirements with the right hardware and architecture. We take a closer look at TOPS, tera operations per second, which is often used as a benchmark for AI performance. When comparing GPUs and NPUs, it is important to understand that not all TOPS are equal. For example, GPU TOPS can differ from NPU TOPS, and FP32 operations are not directly comparable to INT8 operations, since they have very different levels of precision. The same is true when comparing training performance on a GPU with inference performance, or when looking at the total TOPS of a system that combines CPU, GPU, and NPU versus the single TOPS number of an NPU. That's why it is crucial to consider the context. Performance always depends on the application. It's not just about the highest TOPS number, but also about energy consumption, efficiency, and real-world behavior. To make the right decision, you should look for independent benchmarks, carefully check specifications and conditions, and also draw on community experience and specialist forums. And finally, manufacturer specifications should always be read and compared very carefully. So the key message is, don't just look at the TOPS figure alone, always evaluate it in the context of your specific use case. This slide gives you an overview of where different computer models stands in terms of AI performance for different use cases, from anomaly detection to imaging, that play a role in medical applications, measured in TOPS, tera operations per second, and power consumption. At the lower end, we see models like the NXP IMX95 with around 2 TOPS, suitable for lightweight AI tasks such as audio processing, face recognition, or anomaly detection. Moving up, the TI TDA4 VM delivers up to 8 TOPS, enabling more complex tasks such as image or gesture recognition. With 39 TOPS, the AMD Ryzen models are already supporting applications like autonomous robots or surveillance. And at the higher end, the Intel Core Ultra with 99 TOPS provides enough performance for demanding workloads such as medical diagnostics and imaging. So looking further ahead, future generations of ComExpress, ComHPC and Smart models will push into even higher ranges, enabling use cases like diffusion models for image generation, autonomous driving and more. Here we see the software toolchain example from Intel. At the end, the toolchains of the different mentioned silicon vendors are similar. They enable us to bring AI models into medical imaging applications in 3 steps. The process starts with the model. Models can be created in popular frameworks such as PyTorch, TensorFlow, Keras, PaddlePaddle or ONNX. We can also use pre-trained models from industry model, Zeus, or create computer vision models faster with Intel Getty. The next step is optimization. Here we use tools like the OpenVINO model converter to transform models into a format that can run efficiently on different hardware. We can also apply direct model conversion for TensorFlow and PyTorch, or use the neural network compression framework to reduce size and improve speed with quantization, pruning, and sparsity. Jupyter Notebooks provide ready-to-use examples to accelerate this process. Finally, we move to deployment. With the OpenVINO runtime, models can be executed across a wide range of Intel hardware, from Xeon and Core processors to GPUs, FPGAs, and even Atom from low-power use cases. The OpenVINO model server allows models to be deployed over gRPC, REST or CAPT endpoints. This complete toolchain ensures that AI models are not only trained, but also optimized and deployed in a way that maximizes performance, efficiency, and flexibility across different medical imaging devices. Here we see the software toolchain example from Intel. At the end, the toolchains of the different mentioned silicon vendors are similar. They enable us to bring AI models into medical imaging applications in 3 steps. The process starts with the model. Models can be created in popular frameworks such as PyTorch, TensorFlow, Keras, PaddlePaddle, or ONNX. We can also use pre-trained models from industry model Zeus or create computer vision models faster with Intel Getty. The next step is optimization. Here we use tools like the OpenVINO model converter to transform models into a format that can run efficiently on different hardware. We can also apply direct model conversion for TensorFlow and PyTorch, or use the neural network compression framework to reduce size and improve speed with quantization, pruning, and sparsity. Jupyter Notebooks provide ready-to-use examples to accelerate this process. Finally, we move to deployment. With the OpenVINO runtime, models can be executed across a wide range of processor hardware. This complete toolchain ensures that AI models are not only trained but also optimized and deployed in a way that maximizes performance, efficiency, and flexibility across different medical imaging devices. With Cortex A-Ready concept, we simplify the integration of AI into medical applications. A-Ready provides high-performance embedded building blocks that combine AI, IoT, connectivity, and security in one platform. This enables developers to focus on the medical application instead of struggling with complex system integration. The result is much faster time to market. Devices can be prototyped, validated, and deployed more quickly, while still meeting the demanding requirements of the medical industry. So A-Ready is essentially about application readiness, helping customers bring innovative and reliable medical solutions to market faster and more efficiently. Let me close with a quick summary. AI is transforming medical imaging by bringing more speed and precision into diagnostics. Computer models provide the scalable and flexible foundation to integrate these AI capabilities across different medical devices. And with A-Ready, we enable faster time to market by simplifying integration and ensuring efficiency. The goal is clear: to deliver smarter, more efficient medical devices that improve patient care. Thank you very much for your attention.
And thank you, Silke, for that presentation. It's very interesting to see AI used in specific purposes, like in medical applications. So I see that we have a few audience questions coming in, but just a reminder that there is time to ask more questions if you have them in that chat box over on the right-hand side of your screen. So Zoko, are you ready to answer some of the questions that we have so far?
Yes, of course.
So the first question is asking for general information. It says, where can I get the information for the training about SOM and in the case of this presentation, COM development?
So there's a carrier board training for computer model concepts from Congatec. So you can find on the Congatec website the carrier board training with the landing page and all the information to look for a booking and just go in contact with us, and you will be in a session with us in the next training.
So the next question is about hardware requirements. It says, what is the difference in hardware requirements between AI applications for AI training versus for AI inference for medical devices?
Yes, so in the training, for example, for tumor detection, requires very powerful GPUs and TPUs and large amounts of annotated data. So this happens at the end in the data center. And at the AI inference, it's all about real-time and ultrasound analysis. So it's about that it can run on an integrated GPU and NPU with much lower compute demands in real time. So making it ideal for direct use in medical devices. So in the edge AI device, for example, in an endoscopy or ultrasound device, it's about the optimized adjustment between the real-time image with the trained model, and to check if there is a kind of a pattern or detection that you can see in the real-time image.
The next question says, what are the advantages of combining the integrated GPU and integrated NPU for medical imaging? I think you just touched on a little bit of this in your previous answer, but if you could elaborate a little bit more on that.
Yes, so if you have the combination of integrated GPU, and since latest generations of processors, it also has an integrated NPU that was not available in the years before, where you only had an integrated GPU. And now with the integrated NPU as well, it delivers up to more than around 20% higher of AI performance, while reducing also the energy consumption. So this is particularly valuable for a compact or mid-performance device in medical imaging devices, in ultrasound or in endoscopy, to make it more efficient. And the doctor has more time for the patient instead of checking the image, what he can see there, because the AI supports to show the pattern, to show the size of the infection, and so on.
Our next question is asking about memory. It says, what is the RAM size needed for AI inference for edge devices?
So of course, it's up on the real use case. But most of the devices that we see, they have around 32 or 64 gigabyte. And at the end, it needs to be tested. It needs to be tested on the hardware, on the processor module, and the software environment that you're really using on. But that's around the size that we mostly see right now.
The next question, this is a specific use case application, and so the answer may depend on the application, but it says, what will be required in terms of hardware compute power? For example, for mapping a complete path in a medical use case, like making a map of an endoscopy being performed.
So can you just repeat it again? I'm trying
Sure.
to...
What will be required in terms of hardware compute power, and in this case, for example, making a map of an endoscopy being performed?
So what I can say is that in the experience that we see, there are different vendors with their different software environment. And so on the GPU, it's mostly about all the data and the images and the videos. And on the NPU, it's about to make this real time happen. And so what we see is that the NPU part supports with these patterns and with the mapping automated measurements in the image that the doctor has more time to discuss the views and the data with the patient. Did that answer somehow your question, or we also can continue in a later session with that?
And I believe we have time to cover one more question here at the end. And this one is a somewhat high-level question. It says, how do traditional AI performance solutions impact cost, complexity, and power consumption?
So in a use case before latest processors have this integrated NPU, the normal case was that also in AI medical imaging devices or other industrial devices, there was a need for additional GPU card, which is quite expensive and which is not really optimized for this real-time detection or adjustment. So what we see right now is up on the medical use case and the software environment that customers can save now the use of external GPU cards that are connected to the computer model concept device. They can save them because this real-time detection and adjustment of the real image with the trained model can be now done in a more efficient way with the integrated NPU, which is really exactly made for that. And GPUs in general are more made for deep learning. So we see customers up on their performance level, they can save now 1 or 2 external GPU cards in their medical imaging devices, which is around $2,000 to $4,000 or $5,000 of saving in your design costs.
Well, excellent. It looks like we have covered all of the audience questions. Great questions coming in from the audience. And thank you again, Jelko, for the presentation and for the insights during the Q&A.
Thanks too. It was great.
Now, right before we wrap up, I would also like to announce the prize winners for this session. So congratulations to Fred Hendricks and Joel Perry. We'll be in touch with both of you within the next week to make sure that we have the information that we need to send you the giveaway package. In just a moment, you will be redirected to Cogitech's microsite, and I encourage you to check out today's other live sessions, including the next Cogitech session, which is directly following this one, as well as the other keynotes and the published content that are coming online later today. So thank you all once again for attending the All About Circuit Summit Series 2025.